Hi guys, welcome to the learner space on device physics. I'm Ariman. I'll be taking this course, and this is the first module of the first week. And what I essentially want to talk about today, the topic of the module, is a journey from a rock to a thinking machine. And this is just an overview and motivation kind of this course in general. And the word thinking machine in this particular title is something that is more for dramatic effect. At the end of the day, what I really mean is a computer, but I still find it pretty amazing that we were able to literally engineer a rock to behave like a computer. And I think today, not a lot of people would argue that a computer is not very far from a thinking machine. So today I just want to discuss this, how we went through this whole journey and what are the different parts that were involved in this. Right. So firstly, what I want to do is give a roadmap and an overview of this entire journey, and then talk a bit specifically about where what we are learning in this course is going to fit in to this journey. Cool. So basically, we start with a rock. We engineer that rock into something that we call a silicon wafer. And this silicon wafer is a wafer of semiconductor material. And the advantage of this is that we can engineer and embed circuits onto this wafer. Uh, we will come later on to why it is so important to have a semiconductor material make this wafer. The next part to this is the part that is what the basis of our entire course on, which is device physics. And basically, by studying the physics of how this semiconductor operates, we try to design switches using the semiconductor material. And these switches are called specifically are called transistors. The motivation as to why we want to design these transistors or switches is that using switches we can make logic gates, which is something I will talk about today. And using these logic gates, we are able to make memory elements. And the basic motivation is that a computer is basically a combination of switches, logic gates, and memory elements. So the switches are what, of course, they make up the logic gates and therefore the memory elements. And in their own right, they're what control the control logic of the computer, which is choosing between one circuit getting activated and another, for example. The logic gates are what like carry out the all the logical and arithmetic operations of the computers, and memory is like what transfers a memory from one part to another to do a particular operation, right? So for these we need memory elements. So basically, a computer is just made up of these three things, and we have inputs given to the computer, which are like these inputs then go through these circuits made of logic gates, memory elements, and switches, and we get outputs. So, like if you're watching this on your laptop, the inputs that you give to your computer are literally the keystrokes you put in or the mouse clicks, which down the line go and interact with these switches, logic gates, and memory elements. And the outputs are what you see on your screen, right? So there's a lot of complicated like abstraction that happens in the middle, but in a very fundamental sense, this is how a computer works. So the most fundamental problem that we focus on is how do we study the physics of these semiconductor elements to actually use it to make switches, because making switches is the most important thing to do any of the things we spoke about. So this is going to mainly be the focus of this course. Cool. So now I want to get more specific into this journey. So the first step to actually go ahead and make a computer is to make a silicon wafer to design your circuits on. Now, like the starting form of this is that you have quartz rocks that are found in nature. These rocks are eroded to give you silica sand, and this is the form that we start in. We have a lot of metallurgical processes, lot of purification processes that we do to the sand, which is a whole other industry in itself, that gives us pure silicon. And using this pure silicon, we actually again engineer it to make such wafers, which are the building blocks onto which we make our circuits, right? So all circuits, be it in the chips on your phone, like the ICs in your refrigerator, whatever it is, all the circuits are made on these silicon wafers. So the this is the entire metallurgical process that we follow to actually get a silicon wafer on which all our circuits are made. Alright, so now that we have a semiconductor wafer, the next step is to use the properties of this semiconductor to make a switch. Uh, why exactly do we use semiconductors is something that we will talk about when we start studying their physics in more detail. But for now, it's just important to know that there are certain properties that a semiconductor has, which using which we are able to leverage them to make it behave like a switch. So, to talk about making a switch, let's talk about what exactly we mean by a switch to begin with, right? So, I have given a diagram on the top right, and that is literally all there is to it. It is something that has an on state and an off state. The on state is where the switch is closed, the off state is where it is represented as open. In the on state, it allows the flow of current through it freely, and in the off state, it blocks any flow of current. So it does not allow any current to flow across it. uh, like why do we want switches? So we want a way for computers to be able to control the on and off state of these switches, which is crucial for all its operations, right? So any control operation that the computer needs to do, it needs access to these switches and the on and off state. And we will later talk about how these switches themselves become the building blocks towards making any type of logic gate. So even computers doing logic is contingent on these switches. And finally, how we even use these switches to make memory elements. So we want these switches, and we want them, like the computer, to be able to control the state of these switches. The second criteria we need is that we want to be able to fit billions of such switches in a small area, and for them to be able to switch literally billions of times in a single second. Like you cannot even imagine how many chips fit on like one small chip on your phone, and each second how often they're switching. In the old days, computers used to in fact rely on mechanical switches, and they were not at all efficient back then. But to fit the criteria of the kind of computation we need these days, we need the switches to be able to do this. And it turns out that for these criterion, making electronic switches using specific properties of these semiconductors is most suitable, because we are in fact able to make these really small and make them switch really often. So the basic idea is that the smaller you can make them, the more you can have of them, so the more computational power you can have, and the faster you can make them, the faster your computer can do operations. So the entire problem of making your computer better from a hardware perspective is about making a switch that can be smaller and switch quicker and in a more efficient way. So studying the physics of this really will give you an idea of how that is actually done. So the MOSFET is an example of one such switch, and it is the most commonly used switch in the world. So many times talking about designing a switch is considered equivalent to talking about designing a MOSFET. Don't let the full form itself overwhelm you. It's metal oxide semiconductor field effect transistor. Like it'll make sense once we actually get to it. Right. So now just like on device physics, right? So just a informal definition, studying the physics of semiconductor materials and designing and characterizing devices using this physics, and the devices that we design are mainly switches. So this whole branch is called semiconductor device physics, and that is the main focus of this course. Before moving on, I just want to talk about like the black box model of a MOSFET. What does it actually do? Not getting into its inner workings. So how a MOSFET behaves is simple. It has one terminal called the gate terminal. Using a voltage on this terminal, you can control the on or off state of the switch. So if you have a switch at home, you have to manually switch it on or you have to manually switch it off with your fingers. But a MOSFET has, like, because of the physics of the MOSFET, of a semiconductor, we are able to design the MOSFET in a way that we are able to give a voltage to one of its terminals to turn it on or off. So if we give a high voltage to that terminal, for example, it is turned on, and if we give a low voltage to that terminal, it is turned off in one type of a MOSFET. So the main takeaway from this is that uh, just by setting a voltage level or giving a voltage level to one terminal of the MOSFET, we can open or close the switch. And that is the black box model of how the MOSFET works. To get into why it works that way and what are its inner workings and principles is something we're going to do in this course. But just to move forward, because I want to go through this entire overview to give that feel and motivation of the entire process, this is how I want you to think about what a MOSFET is. So the next question to ask ourselves is that can we make this rock actually do logic? Because that will be the real leap. Uh, so as you all know, computers they work on just two logic levels, zeros and ones. And in fact, we represent these logic levels simply by voltage levels. So a zero is just zero voltage and a one is just high voltage. And in when you have two logic levels, the kind of logic operations that you can have are things like and or not, the basic logic operations that you have. uh, Now, uh, at first, this might seem very basic, but even the fact that you can make a computer do these things is a big leap. And secondly, if we figure out a way to do these basic logical operations, we can actually break down very complex computations fully into these operations. So, I'll give you an example. We have a particular circuit made of logic gates. Logic gates being gates like the AND gate, the OR gate, and the NOT gate. That we call a full adder, and that circuit can actually add two numbers in binary. So being able to make such logic gates and do such basic logic, we are actually able to make circuits that can do addition for us. And once we can, in principle, make circuits that can do addition, that can do some basic computation, we can actually use these to do more complicated calculation, right? So once you have a circuit that can add, you can use it repetitively to make a scheme to multiply, for example. So once we are able to show that we can do basic arithmetic with these logic gates, we are actually able to use this to move on to much more complicated, much more abstract stuff. So it's not at all a small deal to be able to do this basic logic, and it is using this that we are able to do all the more complicated stuff. The question then becomes, how do we make the switches that we claim that we are going to learn how to make in these courses? How do we make these switches capable of executing logic? And just to remind you that the stuff that we are doing from here on out is not going to come again later into the course, because we are mainly studying the problem of making these switches. But I just want to give the entire overview so that you can get that motivation of what we are doing. Cool. So now coming to the question of how do we make the switches execute this logic. Okay, so I want to give you a very short teaser on how we can use these switches to do logic. So I'm just going to try and construct with you an AND gate. So for those of you who don't remember, an AND gate is just or AND logic is just something that is one, the output is one only when both the inputs are one. So if any one of the inputs is zero, the output is also zero. So we are going to try and make a circuit using switches that is capable of doing that. And as I've told you, like in the previous slide, the logic level 0 corresponds to 0 voltage or low voltage, and the logic level 1 corresponds to high voltage. Now let don't let the circuit on the right hand side overwhelm you. I'll break each part of it down and show you how we are actually able to implement this AND gate. Cool. So basically, I'll just first tell you all the elements and then I'll tell you how this circuit actually works. So we start with a high voltage source or line on the top. You can consider this to be maybe 5 volts or 10 volts. And we have two switches. Now, what are these switches? These switches are the MOSFETs that I spoke to you about before. And as you can see on the left, I have given a gate to both these switches. So if you remember in one of the previous slides, I told you how the on or off condition of the MOSFET is controlled by the voltage input that is given to these gates. So our A and B are actually the inputs who we want to AND together, and we are actually using these inputs and giving it to the control gate of these MOSFETs. So how these switches will behave is that when A is high voltage or logic level 1, this switch will be closed and current will flow. When B is high voltage, this switch will also close and current will continue to flow. Whichever one of them is low voltage, that becomes an open switch here and an open circuit, and it does not allow current to flow. So I just want you to be very clear on how exactly it is that a switch works. If you give a high voltage to the control gates, which are represented by these lines, to any of these switches, the if it's a high voltage, the switch is conducting. If it's a low voltage, the switch is non-conducting. And that is something I also spoke about before, but I want you to see it in the context of this circuit. And all these lines are, of course, you can think of them simply as wires. Finally, here we have the point where we are taking the output, and the output is connected to the ground across a resistance. You don't need to worry much about what the role of the resistance here is. It doesn't have much of a role. It's just there, right? And finally, this is the point where we are taking the output. So I've just shown you where we are measuring the output. Now I want to show you how this is actually acting like an AND gate. So let's take an example of both the inputs being 1. When both the inputs are 1, both these switches are closed and conduct. If both these switches are closed and conduct, you have a conducting path from the high voltage point to your output point. If you have that conducting path, that means that since it's a purely conducting wire and you don't have any resistance or anything in the middle, the voltage of both these points will become the same. So your output will actually become high voltage because you have a conducting path to the high voltage point. This is why when you have A and B both being high voltage or logic level 1, you get the output also as logic level 1, which is consistent with the 1 and 1 being equal to 1. Let's now talk about if any one of them is 0. If any one, either A or B is 0, the circuit will break at that point because that switch will turn off, because that's how a MOSFET behaves. So if any one of these two are zero, your high voltage point is no longer connected to your output, in which case your output is going to be connected to your ground, which is the low voltage point or zero voltage point, and it's going to have the same voltage as your ground. So if any of these or both of these are zero, your this point is connected to the ground, output point is connected to the ground, and so you have an output of zero. That means if any of your inputs A and B are low voltage or zero, you get an output of zero. And this entirely maps the behavior of an AND gate. So I've shown you here that you can use these switches to actually make an AND gate, and you can think about it, you can read on the internet, you can reach out to me. Similarly, other logic gates can also be made using these switches. I'll give you a quick hint on how you would make an OR gate. Just like here, you have these two switches in series. If you made the switches in parallel and allowed the high voltage to connect to the output through any one of them, that would give you an OR gate. So I just want to demonstrate that we can make all these gates using just switches. And that is the power of a switch. That is how we can actually make this do logic. So as I told you, we can now similarly design other logic gates, and using these logic gates, we can actually do quite complicated logic. So our rock is now capable of doing some serious logical operations. We can also use logic gates to make it possible to do basic algebraic computations, which this rock now becomes capable of. And we can like step these up to more and more complicated computations. Now, I have linked the top three videos. It's like a recap or overview of this stuff if you like don't remember it. The stuff essentially being the binary system, binary addition, and logic gates, so that you are comfortable with it. So if there is any of this stuff that you've learned before but don't remember, you can refer to these resources. The main thing that I wanted to give you guys from this is like to link this video, which shows how you can use just logic gates and make a binary full adder circuit that is capable of adding any two binary numbers. So like if you don't believe me that just using these logic gates you can actually do some pretty serious computations, you can go ahead and watch these videos. All these videos are optional, and I've linked the top three videos mainly so that if you have any doubts you can refer to them and you're able to follow the fourth video. So yeah, if you're interested in how this computation actually happens using these logic gates, you can refer to this video. Cool. Let's move on to memory now. Uh, so the TLDR of this is that we can use logic gates to make memory elements that are able to remember the last value that was stored. Uh, Unfortunately, there is no way that I can explain this in a short or simple way. You can take me for my word that you can do this using purely logic gates. If you are interested in understanding how exactly it happens, I have linked a video which explains it. But basically, we are able to design memory devices using logic gates alone, and these memory devices store the value that you last pushed into them. That's the idea I can give you about it, but how exactly it happens you would have to refer to this video. But the bottom line I want you to take away from this is that using switches we made logic gates, and using logic gates we made memory elements. So now our rock is capable of all these three functions. So now comes the big question, right? That is, can we make a computer, or like I put it in the first slide, can we make a thinking machine? And I'm here to tell you that like how a computer works and computers in general, they're not as scary as they seem. And this diagram that I have put on this page, in principle, is all there is to a computer. So I'm just going to quickly go through that. So I want to first draw your attention to this logic unit that is in the CPU. So the logic unit just consists of different circuits that are capable of doing different logical and arithmetic operations. So we already showed in the last stuff that we can make different arithmetic operations done using logic gates, and we can yeah, basically we can do like quite complicated computations just using logic gates. So different types of computations are just made in this logic unit, and you have different circuits for different types of computation. So you might have a circuit for addition, a circuit for multiplication, etc., etc. So that is all you have in your logic unit. You might have a circuit to select between multiple different options, for example. So that's in your logic unit. Second, which is like kind of the heart of the CPU, is your control unit. What your control unit does is that based on the inputs it gets, it passes these inputs and it chooses different circuits to do different types of computations. So, if your input tells your computer that, hey, I want to do a certain type of activity, the control unit uses switches to actually activate that circuit in the logic unit and deactivate the other circuits. Or if your input tells that pull some value from the memory, I want to add it to some other value and present the outcome, then the control unit has the entire circuitry and the switching to actually go ahead and pull that value from the memory using the wires, the buses, the electronic buses, and activate the circuit for addition. And actually then the circuit for addition does the computation and then push it to the output. So this is all you have to a computer. You have a logic unit that is capable of doing lots of different types of operations. You have input to the computer, which like obviously we put keystrokes, but essentially any program that runs gets it converts all the inputs into assembly code. So the assembly code is the input that the computer receives. The control unit activates different parts of logic and pulls stuff from the memory, does the computation and gives you an output. Now the types of computations done become more and more complex, but it is all built on this same basic fundamental. And the conclusion I want to draw is that all of this is possible using just switches. And that is why we are studying how to make a better switch, and we are actually studying the physics that goes into making a switch. And that is essentially why this course is important. All this stuff is stuff that you can do. You can make computers, but if you can make your switch even 1%, 2%, 5% more efficient, it can have a huge difference in how well your computer performs. So yeah, that is, yes, we can make a computer from a rock. Finally, the next module and going forward. So, this module of the course was just to give an overview of our motivation for why we are doing what we are doing. Next module onwards, we are going to dive straight into the physics of these semiconductor devices, which is, I guess, why you're here in this course, right? And the main objective of this course is to use and understand the fundamental physics to design a switch. And at the end of the course, we are going to study the design of a switch, and I'm going to give you guys a simulation assignment to actually go ahead and design it. That is what we are going to be working towards from the next module onwards, and I hope to see you there.